Most locomotives are built to move trains. The EMD SW1500 was built to survive. For more than 50 years, these switchers have worked in the harshest environments railroads can offer: classification yards, port terminals, refineries, steel mills, and countless industrial sidings, where locomotives age fast and die early. While their contemporaries were retired, scrapped, or relegated to museum pieces, the SW1500 just kept going. Today, hundreds remain in active service, performing the same grueling work they were designed for in 1966. This isn't a story about horsepower or speed records. It's about why one of EMD's most conservative designs outlived nearly everything around it, and what that tells us about locomotive engineering when survival matters more than specifications. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. To understand what made the SW1500 exceptional, you need to understand what kills yard locomotives in the first place. Yard work destroys machinery in ways that long-haul operation never does, and most rail fans never fully grasp just how brutal this environment actually is. Start with the mechanical reality. A yard locomotive performs hundreds of coupling operations every shift. Each one sends a shockwave through the entire structure, through the coupler, draft gear, underframe, bolsters, and into the trucks. This isn't the smooth, steady force of pulling a train across open territory. It's repeated impact loading, and it fatigues metal faster than almost any other service pattern. Then there's the constant starting and stopping. Road locomotives accelerate, reach track speed, and maintain it for miles. Yard locomotives operate in a perpetual cycle of acceleration, braking, acceleration, braking. The traction motors never settle into steady operation. They're constantly being loaded and unloaded, heated and cooled, stressed and relaxed. This cycling is murder on electrical insulation, motor bearings, and gearing. The thermal environment is equally destructive. Diesel engines are designed to reach and maintain operating temperature. In yard service, that rarely happens. An engine starts cold, idles while the crew line switches and couples cars, loads up briefly to move a cut, then returns to idling. The constant transition between thermal states creates expansion and contraction cycles throughout the engine block, cylinder heads, and exhaust manifolds. Gaskets fail, seals leak, metal fatigue accumulates invisibly. Low-speed operation creates its own problems. At track speed, airflow through radiators is abundant. In a yard, locomotives creep along at 2 or 3 miles per hour, sometimes less. Cooling fans work harder to compensate, and even then, components run hotter than they would at road speed. Traction motors, in particular, suffer. They generate heat whenever they're under load, and at low speeds, there's minimal airflow through their ventilation systems. The environmental conditions are equally unforgiving. Yard locomotives work in dust, oil mist, chemical fumes, and extremes of temperature. They operate in steel mills where heat radiates from molten metal. They work in ports where salt air corrodes everything. They serve refineries where hydrocarbon vapors permeate the atmosphere. None of this appears on a specification sheet, but all of it determines whether a locomotive lasts 5 years or 50. Many switchers built in the 1950s and 1960s failed early, precisely because they weren't designed for this reality. Some used engines optimized for road service, high revving, lightweight, powerful, but intolerant of constant thermal cycling. Others incorporated electrical systems too delicate for industrial environments. Still others used lightweight frames that cracked under repeated coupling shock. The specifications looked impressive. The operational lifespan was disappointing. The SW1500 emerged from a very specific understanding of what yard service actually required. EMD had been building switchers since the 1930s, and by the mid-1960s, they understood something fundamental. Yard locomotives don't need to be impressive. They need to be unkillable. The horsepower rating itself reflected this philosophy. 1,500 horsepower wasn't chosen to compete with anyone or break records. It was chosen because it represented the optimal balance between capability and durability for yard work. It provided enough tractive effort to handle heavy cuts of cars on level ground and modest grades, but not so much power that wheel slip became a constant problem, or that the drivetrain operated near its stress limits. This was a deliberate step back from the industry trend. In the 1960s, railroads were demanding more horsepower in road locomotives. The logic was simple. More power per unit meant fewer locomotives per train, lower operating costs, higher productivity. EMD applied that thinking to road units like the SD40 and SD45, and it worked brilliantly. But they didn't apply it to switchers. The SW1500 was actually less powerful than some earlier EMD switchers. The SW1500 produced 1,500 horsepower. The earlier SW1200 produced 1,200 horsepower, but the model line before that, the NW5, was rated at 1,000 horsepower when it debuted in 1946. EMD could have easily built a 2,000 horsepower switcher in 1966. They chose not to, and that choice was everything. The design goal was explicit: create a locomotive that could run all day at low speed, absorb coupling impacts without structural damage, and be repaired quickly with parts any diesel shop already stocked. There was no attempt to innovate for innovation's sake, no experimental electronics, no exotic materials, no weight-saving measures that might compromise strength. The SW1500 was conservative engineering by design, and that conservatism was its greatest strength. EMD also understood crew psychology. Yard crews don't want excitement. They want predictability. They want a locomotive that starts reliably, responds consistently to throttle inputs, brakes smoothly, and doesn't surprise them. The SW1500 delivered exactly that kind of boring reliability, and boring reliability is what keeps locomotives working for decades. The mechanical design of the SW1500 reveals why it survived when others didn't. Every major system was built with survival, not performance, as the primary criterion. The heart of the locomotive was the EMD 12645E engine. This was a 12-cylinder version of EMD's 645 engine family, the same basic design used in road locomotives like the SD40. But the application was entirely different. In a road unit, the 645 engine might be configured as a 16-cylinder or 20-cylinder variant, producing 3,000 or even 3,600 horsepower. In the SW1500, it was deliberately detuned. 12 cylinders producing 1,500 horsepower meant each cylinder was working well within its capacity. The engine operated at lower peak pressures and temperatures than it would in a higher output configuration. This single factor extended component life dramatically. Piston rings lasted longer, valves lasted longer, bearings lasted longer. The engine didn't wear out, it aged gracefully. The 645 engine was also exceptionally forgiving of poor operating conditions. Its roots were in EMD's earlier 567 engine, which had proven reliable across millions of operating hours in every conceivable environment. The 645 refined that design, but retained its fundamental tolerance for abuse. It could handle dirty fuel, inconsistent maintenance, extended oil change intervals, and thermal cycling that would have destroyed more highly tuned engines. The electrical system was equally deliberate in its simplicity. The SU1500 used direct current traction motors, proven technology that dated back to the 1930s. By 1966, some manufacturers were experimenting with more sophisticated electrical systems. But EMD stuck with what worked. The DC system was straightforward to troubleshoot. Parts were universally available, and failure modes were well understood by every diesel electrician in the industry. There were no computers, no solid-state controls. The transition relays that controlled motor connections during acceleration were electromagnetic devices, big, heavy, brutally simple. When one failed, you could see the damage, order a replacement, and install it with hand tools. This made the SW1500 maintainable anywhere by anyone with basic diesel locomotive training. The frame construction was massively overbuilt by modern standards. The underframe was a welded steel structure designed to absorb and distribute coupling shock without flexing. Where lighter switchers might crack their frames after years of impact loading, the SW1500 frame simply endured. The bolsters, the crossmembers that connected the frame to the trucks, were similarly robust, providing a solid foundation that kept everything aligned even after decades of abuse. The trucks themselves were optimized for low-speed adhesion rather than high-speed stability. The flexi-coil trucks used on the SW1500 featured a multi-axle suspension system that kept all wheels in contact with the rail even on uneven track. This mattered enormously in yard service, where tracks might be poorly maintained, covered in debris, or degraded by constant switching movements. Good adhesion meant less wheel slip, less wasted energy, and less stress on the electrical system. Cooling capacity was another area where EMD deliberately overbuilt. The radiator section was larger than strictly necessary for 1,500 horsepower in road service. This excess capacity meant that even during extended low-speed operation, with minimal airflow and high ambient temperatures, the engine stayed within safe operating limits. Overheating, a chronic problem for undercooled switchers, simply wasn't an issue. Here's something most discussions of locomotive longevity miss. Wear isn't about calendar time. It's about stress cycles. A component doesn't fail because it's old. It fails because it's been stressed and relaxed, heated and cooled, loaded and unloaded too many times. The SW1500 lasted because its components accumulated stress cycles more slowly than those in comparable locomotives. Consider the diesel engine. Every time an engine goes from idle to full power, every cylinder experiences a stress cycle. The combustion pressure rises, the piston accelerates, the connecting rod flexes, the crankshaft bends slightly under load, then the throttle comes back, and everything relaxes. Do this enough times, and metal fatigue accumulates. Eventually, something cracks. In a road locomotive, this happens constantly. The engineer notches up to run 8, holds it there for miles, then notches down for a speed restriction or grade change, then back up again. The engine cycles through its load range dozens or hundreds of times per trip. In a yard, by contrast, the SW1500 rarely saw full throttle. Most switching moves required only partial power. The engine operated in the middle of its range, where stresses were lower and components stayed well below their fatigue limits. The same principle applied to traction motors. These machines generate torque by passing current through their armature windings. The current creates heat. The heat is removed by ventilation and internal cooling passages, but the heating and cooling cycles cause expansion and contraction, and eventually the insulation between windings breaks down. This is called thermal cycling failure, and it's one of the most common ways traction motors die. The SW1500 experienced fewer and less severe thermal cycles than road locomotives. It operated at lower speeds, which meant lower continuous currents and less heat generation. It also spent more time idling, which allowed components to cool down between operating periods. The net result was that traction motors lasted longer, not because they were better, but because they were stressed less severely. Frame fatigue followed the same pattern. Every coupling impact sends a stress wave through the frame structure. If the impact is severe enough, it can cause microscopic cracks at stress concentration points, bolt holes, weld joints, changes in cross-section. Over thousands of impacts, these cracks propagate, and eventually the frame fails catastrophically. The SW1500 absorbed these impacts through its heavy underframe and robust draft gear. The forces were distributed over a larger structure, which meant lower peak stresses at any given point. More importantly, the locomotive's low operating speeds meant coupling impacts were less violent to begin with. A 5-mile-per-hour coupling creates far less stress than a 10-mile-per-hour impact, and the difference compounds over 1 million coupling operations. This advantage in stress accumulation created a virtuous cycle in maintenance. Because components degraded slowly, problems appeared gradually rather than suddenly. A mechanic might notice that a traction motor was drawing slightly more current than normal, or that an engine cylinder wasn't developing full compression, or that a truck bearing was running warm. These early warnings allowed intervention before catastrophic failure occurred. Contrast this with higher-powered, more highly stressed locomotives, where failures often came suddenly. An overstressed component would run fine, then fail completely with little warning. The repair costs were higher, the downtime was longer, and the cumulative effect was a shorter service life. Modern switchers, ironically, often fail to match this longevity precisely because they're more sophisticated. They produce more power from smaller packages, which means higher stresses. They incorporate electronics that improve efficiency but add failure points. They're optimized for lower emissions, which sometimes means operating closer to thermal limits. The specifications look better on paper. The service life is often shorter in practice. Understanding the SW1500's longevity requires understanding what railroads actually did with them. These weren't glamorous assignments. They were the grinding, repetitive work that keeps freight networks functioning. The primary role was classification yard switching. In a hump yard, the SW1500 would push cuts of cars over the hump, where gravity took over and the cars rolled into their assigned tracks. In flat-switched yards, it would assemble and disassemble trains car by car, pulling cuts from arrival tracks, sorting them by destination, and building outbound trains. This work required precise speed control, good low-speed tractive effort, and above all, reliability. Delay a yard switcher, and you delay every train that needs its services. Industrial leads were another common assignment. Many large industries, as steel mills, automotive plants, chemical facilities, maintained their own rail networks. The SW1500 would deliver inbound cars and collect outbound ones, often working in tight clearances with sharp curves and poorly maintained track. The locomotive's compact size and excellent low-speed control made it ideal for this environment. Port terminals used SW1500s extensively. Container operations, bulk cargo facilities, and intermodal yards all required locomotives that could move cars short distances, spot them precisely at loading docks, and do it all day without breaking down. Salt air and heavy use made this a particularly demanding environment, but the SW1500's simple, robust design handled it well. Transfer runs represented another niche. Some SW1500s spent their entire careers moving cuts of cars between nearby yards, or between a classification yard and an industrial district. These weren't long runs, perhaps 5 or 10 miles, but they required a locomotive that could handle cuts of 20 or 30 cars on grades and curves, then switch them at the destination. Railroads kept these locomotives in service for a simple reason. They knew exactly what they were getting. Fuel consumption was predictable. Maintenance costs were predictable. Availability was high. Crews trusted them. When a railroad needed to move cars in a yard or industrial setting, assigning an SW1500 meant the work would get done without drama. As railroads consolidated and traffic patterns changed in the 1980s and 1990s, many SW1500s entered second and third careers. Short-line railroads bought them, often at attractive prices, and put them to work on branch lines and local freight runs. They were understressed for this kind of work. 1,500 horsepower is more than adequate for a 15-car local freight, which meant they continued to age slowly, even in new roles. Leasing companies acquired SW1500s and rented them to industries and railroads that needed temporary motive power. Industrial operations bought them outright and ran them for decades on private trackage. Some were rebuilt with updated electrical components or even repowered with different engines, but the basic platform proved adaptable enough to justify the investment. Crews who operated SW1500s regularly rarely had much to say about them, and that was the highest compliment. It would start when you turned the key. It would pull whatever you coupled it to, within reason. It would stop when you applied the brakes. There were no quirks to learn, no special procedures to remember, no personality to manage. For yard work, that boring predictability was exactly what everyone wanted. The SW1500 didn't win on specifications. It won on survivability, and that victory reveals something uncomfortable about modern locomotive design. When EMD introduced the SW1500 in 1966, the railroad industry was entering a period of rapid technological change. AC traction systems, microprocessor controls, and advanced diesel engine designs were all on the horizon. The assumption was that these innovations would produce locomotives that were not only more powerful and efficient, but also more durable. That assumption was only partially correct. Modern switchers are indeed more efficient. They produce fewer emissions. They offer better tractive effort per horsepower, but they don't necessarily last longer, and in many cases, they require more intensive maintenance to achieve even comparable lifespans. The problem is complexity. Every electronic component is a potential failure point. Every sensor that monitors engine performance can malfunction. Every software-controlled system requires updates, troubleshooting, and specialized knowledge. When these systems work, they work brilliantly. When they fail, they often require factory support, proprietary diagnostic tools, and components that aren't interchangeable across different locomotive models. The SW1500, by contrast, could be maintained by any competent diesel mechanic with a service manual and basic tools. There was nothing proprietary about its design. DC traction motors were universal technology. The 645 engine was used across dozens of locomotive models. Bearings, gaskets, filters, and electrical components could be sourced from multiple suppliers. This made the locomotive maintainable anywhere, by anyone, indefinitely. Economics also changed. In 1966, railroads expected locomotives to last 30 years or more. Today, financial models often assume shorter service lives. Leasing arrangements, tax considerations, and technological obsolescence all push toward replacing equipment more frequently. A modern railroad might find it more economical to lease new locomotives every 10 years than to maintain older units indefinitely, even if those older units are still mechanically sound. But here's the uncomfortable truth. Railroads still need what the SW1500 provided. They need simple, durable switchers that can work in harsh environments without constant attention. They need locomotives that mechanics can fix quickly without specialized training. They need equipment that doesn't become obsolete the moment the manufacturer releases a new software version. The modern equivalent of the SW1500, if it existed, would probably look very different. It might use AC traction for better low-speed performance. It might incorporate selective catalytic reduction for emissions compliance. It might offer remote control capability for one-person switching operations. But at its core, it would need to embody the same philosophy: survival first, specifications second. Some railroads recognize this. They kept their SW1500s running long after newer switchers were available, precisely because the older locomotives just worked. Maintenance crews knew them. Parts were available. The locomotives fit into operational patterns that hadn't changed in decades. Replacing them meant disruption, retraining, and uncertainty about whether the replacement would actually be better. The SW1500 didn't survive because railroads were nostalgic or conservative. It survived because it solved a specific problem better than anything that came after it. That problem was simple. How do you build a locomotive that can work in terrible conditions, day after day for decades, without requiring heroic maintenance efforts or sophisticated support infrastructure? EMD answered that question in 1966, and the answer turned out to be more durable than almost anyone expected. The SW1500 wasn't the most powerful switcher. It wasn't the most innovative. It wasn't even the most efficient by modern standards. But it understood its job better than almost anything else on rails, and that understanding kept it working long after its contemporaries were gone. Today, hundreds of SW1500s remain in active service, more than 50 years after the first ones were built. They work in short line yards, industrial plants, port terminals, and rail-served facilities across North America. They're not relics, they're not museum pieces, they're working locomotives doing exactly what they were designed to do, in exactly the way they were designed to do it. That's not nostalgia, that's engineering done right.